A model's ability to absorb and store information is dictated by its capacity, the total number of parameters available for data retention. In a traditional dense architecture, every parameter in a layer is activated for every token in an input sequence. If you feed the model a single word, the entire mathematical weight of the system is engaged to process it. This creates a quadratic computational penalty. As you increase the size of the parameter matrices to gain capacity, the number of mathematical operations required to train and run the model scales at a much faster rate than the capacity itself. This results in a flops bottleneck. Flops, or floating point operations, measure arithmetic work performed by a processor. In dense models, compute required for a forward pass quickly exceeds the limits of available hardware. Training a trillion-parameter model under this dense paradigm is physically impossible with current technology. Memory and power to activate that many parameters simultaneously would overwhelm the world's largest computing clusters. Brute force scaling of dense layers has reached a dead end. Surpassing these limits requires a structural change that moves away from the all-at-once activation of parameters. To break the link between parameter count and computational cost, researchers have turned to conditional computation. The core objective is to leave the vast majority of the network idle, dynamically activating only the specific subcircuits needed for a given input. This theory is physically realized through the sparsely gated mixture of experts layer, or MOE. Here, a single monolithic layer shatters into an array of parallel subnetworks. Each expert is simply a standard feed-forward neural network. Instead of one large block of parameters, we have hundreds or thousands of smaller, isolated ones. A new gating network acts as a traffic controller. It evaluates each incoming token and determines which specific experts are best equipped to handle it. This unique architecture allows for a trillion-parameter model that only spends a billion parameters worth of compute on any single word. By decoupling the total parameter count from the active computational footprint, the MOE architecture allows models to scale in size without a proportional increase in the hardware required to run them. Routing uses noisy top K. Multiplying the input token by a gating matrix generates raw scores. Gaussian noise forces network exploration. A softmax function creates a normalized probability distribution. Finally, a sparsity constraint keeps the top two probabilities, forcing the rest to negative infinity. Because the unselected experts receive a gate value of 0, the system performs no mathematical operations on them. This ruthless filtering is the only mechanism that prevents the quadratic compute penalty from making a trillion-parameter model untrainable. When certain tokens are consistently routed to the same subnetworks, those experts begin to adapt to the specific patterns of that data. In his 2017 research, Noam Shazir discovered that this process leads to organic, unsupervised clustering. No human programmer tells the model which expert should learn which rule. The specialization is a byproduct of the mathematical routing itself. Semantic clustering maps this as tokens group around specific nodes. Expert 381, for example, specialized to handle the article "a" only when introducing leadership nouns like a leading role. In contrast, Expert 2004 evolved to process speed-related adverbs like rapidly or drastically. This emergent specialization transforms the model into an ensemble of micro-specialists, each focused on a narrow domain of language, allowing for higher accuracy than a general-purpose dense layer. However, theoretical routing faces a systems failure known as the shrinking batch problem. If the router finds one expert slightly more useful than the others, it can collapse the routing, sending every token to a single node. The hardware memory for that node overflows, causing the entire training run to fail. Engineers solve this using an auxiliary load balancing loss. This is an additional mathematical penalty that discourages the router from favoring any single expert, forcing it to distribute tokens across the hardware cluster. Physical constraints also dictate the architecture. Even a single large expert can exceed the memory of a single accelerator chip. Researchers handle this using mixed parallelism. Standard layers are replicated, while individual experts are physically sharded across different devices in the processor mesh. Tokens hitting the MOE layer fire across the high-speed network to their assigned expert, process, and return to the main sequence. Successful scaling of these models is as much a feat of distributed hardware engineering as it is a breakthrough in neural architecture. The results of this engineering are clear when comparing sparse MoE models directly against their dense counterparts. This chart compares test perplexity, where lower is better, against the computational budget. For the same amount of mathematical work, the green MoE models achieve significantly lower perplexity than the blue dense models. When we look at parameter count, we see the true capacity advantage. The hierarchical MoE models continue to improve as they reach into the billions of parameters, while requiring very little additional compute. These efficiency gains translate to real-world tasks. Sparse models achieve higher BLEU scores in translation without increasing the active parameter count during inference. The empirical data proves sparse conditional computation is the most efficient path to scaling model capacity. These principles led to the creation of G-shard and the switch transformer. These models pushed the architecture to a scale of 1.6 trillion parameters, distributed across 2,048 TPUs. Because compute per token is decoupled from total size, these models reach convergence in days, a task that would take dense models months to complete. We now have a pipeline where text enters, the router identifies the optimal pathway, the TPU mesh handles the distributed computation, and the specialized output is recombined instantly. The challenge of scaling deep learning has shifted. Success is no longer found in the brute force activation of ever larger dense layers, but in the efficiency of the routing logic that connects tokens to experts. Instead of firing every parameter for every word, we now have artificial intelligence systems that precisely route signals only to where they are needed.